Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over how to solve a radioactive decay kinetics problem. Basically, if you're given a radiometric sample that degrades or decays over time, how much is left or how long does it take to get a certain amount and things like that. So let's get into this. So in this problem, we have a sample that initially contains 1.6 moles of a radioactive isotope. So they're giving us the initial amount, and they want to know how much of the sample remains after 4 half-lives. So what do? We could use these two equations right here. We do know we don't know the half-life though. They're not giving us the half-life. Uh, so we can't really use the half-life to figure out what K is and therefore plug that in. So we're not able to use these two, but these two can be combined into this one, and notice K is gone. We don't have to worry about K, and but it does have the half-life. Now we're not given the half-life, but here's a secret. Here's a key to this problem. Notice that they give us an even number of half-lives, right? They tell us it's 4 half-lives. It's not 1.5 lives. It's not 3.25 half-lives. It is 4 half-lives. We can still use this equation. So, and even if it wasn't like a whole number of half-lives, if it was a fractional number of half-lives, we could still use this equation. Why? Well, in here we have the total amount of time divided by the half-life, right? So if we're given a certain amount of time that elapsed, and we're given the half-life of our radioisotope, we would divide the two, and what would that give us? That gives us the number of half-lives that have been completed over that particular amount of time. And that could be a whole number, it could be a fractional amount. So this division here, this fraction here, is the number of half-lives. So we're given 4 half-lives, so we can substitute in for this fraction the number 4. So if we do that, then we get the amount we have after a certain amount of time is going to be equal to the initial amount. And the initial amount, let me write this down here. So the initial amount that we're starting with is 1.6 moles of this radioactive isotope. This fraction here, the time elapsed divided by the half-life, is the total number of half-lives that has elapsed. So we know that. We're given that 4 half-lives has elapsed. So that's going to be T over T1 half. This fraction is 4. So this is the number of half-lives. So we're given the number of half-lives. So this fraction is 4. And we're trying to find the amount left over. So we have everything we need. So we plug this into our formula here. NT, the amount left over, is equal to the initial amount, which is 1.6 moles. And that's multiplied by 1/2 raised to what power? The power of 4. So all I have to do is plug this in, solve for NT. So what is 1/2 to the 4th? So 1/2 1/2 to the 4th, let me get this right, is equal to 0.0625. So 1.6 moles times 0.0625. And so when I do that, I get 0.1 moles left. Now, that's one way to do it, but I didn't have to do it this way. I actually did not have to use this equation because notice that it says 4 half-lives. If you know what a half-life is, then you can just use that to figure out how much is left. Well, what is a half-life? A half-life is defined as the amount of time it takes for half of your substance to disappear, right? So if you're going through 4 half-lives, then after each half-life, you have 1/2 less of what you had previously. So if my original amount was 1.6 moles, then this goes through 4 half-lives. So all I have to do is go through and divide by 2 for every half-life. So to go from 1.6 to the next half-life, I divide that by 2, right? So I take 1/2 of 1.6, and that's 0.8 moles. And then that's the first half-life. So half-life number 1. And then I go through half-life number 2. I divide that by 2. Again, I take half of that. So that's going to be 0.4 moles. And then I go through a third half-life, and I take half of that. That's going to be 0.2. And then finally, I go through another half-life, 4, and half of that is 0.1. So I didn't need to use this equation. All I needed to use was the fact that I have 4 half-lives. I know a half-life is the time it takes for half of it to disappear. So if I'm going through 4 half-lives, then it's going to be cut in half 4 times. And so you just do that. So then that is a second way you can do that. This only works if you have a whole number of half-lives. If you have a fractional amount of half-lives, it's not going to work. You need to use the equation. But all you do is you put in the fraction, right? So let's say, for example, instead of 4 half-lives, it was 4.5. Then you just put 4.5 for your ratio, right? So that's how you use this equation. Oops. Sorry about that. All right, so that is how you attack these sorts of problems. So remember, if you have a whole number of half-lives, not the half-life itself, but a whole number of half-lives that the substance or sample is going through, then you can just divide your sample, the original amount, and divide it that many times to get your answer. Or if you like, you can use the equation. That's fine too. So you do you, whatever works, whatever floats your boat. All right, so that's it for this video. I hope you found this entertaining. I hope you found this useful. And if so, then please like the video, share the video with your friends, hit that like button. Also, make sure you subscribe to my channel, hit that notification bell. And when you do, make sure you click all so you can be notified by all the videos I put out. And finally, please put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me, and have a great day.